All right. Let's discuss the tournament predictor. So you have this. So we have this table, okay, which is maintaining information about whether you should use the global or local predictor. Okay. Now, what it's indexed using the 12 bits of your current branch address. So you have come to a branch, right? And you need to know whether this branch needs to be taken or not. Sorry. So you take the 12 bits of the branch address, index into this table. So because you're using 12 bits of the branch address, there are 4K entries in the table, or the reverse. Because there are 4K entries in the table, you need to use 12 bits of the branch address. Now, so it'll be something like this. If it's 00 value in the entry, it says use local predictor. Okay. If it is 11, it is use global predictor. If it is 10, predictor is saying, of course, take global, use the global predictor. You could be wrong. Okay. You could be wrong. And if you are wrong and you are actually supposed to take the local predictor, this value will be changed to 01. Okay, so your prediction will change to predicted to be taken local predictor. Okay, that's the purpose of this 2-bit predictor here, whose purpose is to determine whether this branch should use the local or the global predictor. Okay. Now, the global predictor maintains a global history of the last 12 branches. Okay. In our previous example, we saw it maintains a history of the last 2 branches. Here, they are maintaining a global history of the last 12 branches. Now, you use that value. So, this is a shift register here, right? You use that value to index into this table of 4K entries. Okay. And each entry in this 4K, in this global predictor is a 2-bit predictor. Okay. So you have basically the usual 2-bit predictor here, but which is indexed by the last 12 branches outcome. Okay. So if it is 00, it's predicted not taken. 10 predicted taken, but 1 not taken will take you to 01. Okay. 1 taken will take you to 11. Okay. So if it is 11, you are at a saturated value of predicted taken, and so on. Okay. The local predictor. Okay. This is the local predictor. It uses the last 10 outcomes of the branch. So far, we never saw this. We said in so far, whether it is 1-bit predictor, 2-bit predictor and all, that we will use the bits in the branch address to index into the branch history table, right? But here in this local predictor, they are using the last 10 outcomes of the branch to index into the table. So essentially, this is the local history. They're maintaining a local history of the branch and using that information to, sorry, I'm really sorry. Actually, no. This is the 1K entries. So they're using 10 bits. Okay, they're using the 10 bits of the branch address to index into this table. What does this table contain? This table contains the last 10 outcomes of the branch. Okay, so they are not maintaining a predictor in this table. What they are maintaining in this table is the history of the outcome of that branch. Okay, and then they use these 10 bits. Okay, they use these 10 bits, which are the history of the branch, as index into this table, which is the actual predictor table. And the predictor table is a 3-bit predictor. So far, we have seen 1-bit or 2-bit predictor, but this is a 3-bit predictor. Since we are using the last 10 outcomes of the branch, the number of entries in this table is 1K. Okay. So how do we get all the 29K entries? This is 4K into 2 bits. The first table is 4K into 2 bits, 8K. The global predictor is 4K into 2 bits, which is another 8K. Then you have this predictor, this table containing the history of the branch, which is 1K into 10 bits. And then you have the actual predictor table, 1K into 3 bits. Add them up, you'll get 29K. That is what is the predictor in the alpha. Okay. Any questions on this? Tournament predictor, are you clear about what's happening? Your book doesn't have this figure. They just give a description. I have sent Bansi the description, the complete description, which is missing in the 5th edition. So hopefully the figure makes it clear to you how it's working. No questions? Okay. If there are no questions, then we come to the branch target buffer. So this is from chapter 3, right? All these things that I'm talking about, the correlating predictors, the tournament predictors, are there in the chapter 3. But they are at the beginning of the chapter 3, and branch target buffer and the next thing that I'm going to talk about are almost at the end of the chapter. Okay. So I decided after a lot of thought to finish off all branch optimizations at one shot, then take up the actual instruction level parallelism. How do you improve pipelining, right? How do superscalars work and manage to do much more work than what they can do if you look at dependencies? Okay, so that part is coming up, but I thought I'll finish the branch optimizations. So by the way, I know we are almost close to finishing off the time, 3 o'clock, but are people willing to, stay on so that we can finish branch optimizations today? The reason is Friday is a holiday. Okay, so there will be no class on Friday. And I have put up the next 2 videos on the course page. I want you to go through those videos for the next Tuesday's class. And so if I finish off the branch optimizations today, it will be sort of useful for you to go through those videos.
Ma'am, actually, some of us are having exam like 4 to 6.
Okay.
So, like, it's okay till 4, but after.
No, I won't be taking up to 4.
Okay.
I have branch target buffer and then return address predictor, that's all. So it won't take long. I just wanted to make sure another 15 minutes extra will not be a problem for people. Okay, so let's look at the branch target buffer. As you know, so far what all we have talked about is essentially saying, is the branch taken or not, right? We are predicting whether the branch is taken or not. Fine, we'll say branch is taken. Let us say we are 100% accurate. But unless we know the target address, target instruction address, we can't fetch the right instruction even though we know that it's going to be taken, right? So what are we achieving if we can only predict but cannot actually know where to fetch the next instruction from? Okay. To solve this problem, they have the branch target buffer. So it's a very simple idea. You have a instruction to fetch. So currently this is the instruction you are fetching. Okay. This instruction can be a branch instruction, agreed? you're fetching an instruction. That instruction can be any instruction. It can be an add, divide, multiply, or it can be a branch instruction. If it is a branch instruction, we need to know two things. Is it going to be taken? And if it is going to be taken, what is the target address that I have to next put into the PC? So they use the PC of the current instruction which you are fetching as index into this table, or not so much index, but actually look up in this table. Okay, because the table here, this part is consisting of the the address of the instructions. Okay. Now, if that instruction is found, that address is found here, then this will be the predicted PC. So this is the PC that will be the next PC is what you are predicting. You can also have, of course, the branch prediction information here. So you can have a 2-bit branch predictor in this table. So the branch prediction bits will tell you whether the branch will be taken or not. If it is taken or not taken, this PC, predicted PC will give you the next PC value. And so now let's look at the, flow chart. As you can see, this PC is sent to both the memory to fetch the instruction, right, into the instruction register, as well as to the branch target buffer. Okay. And if the entry is found in the branch target buffer, you send out the predicted PC next on the address bus. And if it is a taken branch is correctly predicted, and therefore you can continue with your execution. But if it's not a taken branch, then this is a mispredicted branch. Okay. So whatever instruction you have fetched is wrong, convert it into a no-op. Then you delete this entry from the branch target buffer because it's not a taken branch. And continue. If the entry is not found in the branch target buffer, if it is a taken branch, okay, if it is a taken branch, then enter the branch instruction into the branch target buffer along with what is the target PC. Okay, if it's not a taken branch, it's a normal instruction, so there's nothing to do. All right, and they have marked here which part of this flowchart is executed in which stage of the pipeline. Okay, so it's a very simple technique, but which really improves the performance of the processor. So as soon as you fetch an instruction, or while you are fetching the instruction, at the same time you're looking at the branch target buffer, and if it is if it's a taken branch, it will be found in the branch target buffer. The predicted PC will be there. So you just set your PC to that predicted PC value instead of doing your standard calculation on your PC, right? Normal calculation on PC is PC equal to PC plus 4. Instead of that, you simply set the PC to the predicted PC value, and so in the next clock cycle, you will fetch that instruction. But if your prediction is wrong, delete the entry from the branch target buffer and proceed. If you are fetching an instruction, it is a branch, but it is not found in the branch target buffer, and the branch is taken, then insert it into the branch target buffer, so that on the next next execution of the same branch, at least you will not have any stalls. Okay, so that's the purpose of the branch target buffer. Any questions on that? So the final thing is a return address predictor. Actually, this is very normally done in your OS. You should be knowing. We say that when you're calling a function, you push the return address from the function in onto the stack. We discussed this during our instruction set principles also, right? Because in the video he talks about how the stack is set and all that, right? Saving and restoring registers. So here, what we are doing, we have a small buffer, okay? Every time there is a function call, you push the return address onto that buffer, okay? Whenever you exit from the function, you simply pop the value and make that the PC, okay? So, return values, returning from a function then becomes very easy, and you are always able to return to the right instruction without any delay. All right. And if this buffer, the depth of this buffer is equal to the depth of your function calls. That is, we please note that many times we tell you when you're doing programming, of course, not during your introductory programming course, but I think in your OS course, you should be warned actually that you can't, have infinite depth of functions. The reason being that you'll run out of stack space in your process. Okay. So, but if you have a reasonable depth to the, how many functions are being called from a single function, so you keep calling function from function from function. If the depth of that is reasonable and is equal to the depth of this buffer, then you have absolutely accurate prediction on the return address from the functions. So you don't lose anything absolutely in terms of clock cycles. Okay, so that is the return address predictor, and it gives you regular branch predictors don't do very well on returns from functions. Therefore, having a return address predictor separately as a separate buffer, which is like a stack, is very important to reduce mispredictions on returns from functions. Okay. So in summary, a branch prediction is very, very important, especially for superscalar processors, right? Single predictor will always mispredict twice in a loop. So we go to a 2-bit saturating counter, which is normally used, but they can also use a 3-bit predictor. Not more than 3 bits are used in the predictors normally. The behavior of some branches is based on the outcome of other branches, whereas some branches are based solely on their own outcomes, right? So a tournament predictor will be, used to predict whether a branch should use local predictor or a global predictor. Okay. And tournament predictors are what are the state-of-the-art predictors in processors today. All right. So that's basically the thing. And to improve the performance of branches, we need to know the target address also. So here's where the branch target buffer comes into picture. And since typical branch predictors are very poor at predicting the return address from functions, we maintain a small buffer as a stack for the return address predictor. All these together make sure that most of the time your branches are not mispredicted. You don't have to introduce stalls into your pipeline and help improve the performance of your processor. Okay, so that's about branch optimizations. And on Tuesday, no, not Tuesday, yeah. So next Tuesday, I'll be talking about compiler-based optimizations, and you will have time until next Friday to see the videos, the 2 videos I have put up, and we can discuss anything you have on those videos next Friday. Okay. All right.